What's happening, everyone? Welcome back to my first video in quite some time. We're going to do my favorite math proof ever, and it's going to deal with infinities. Technically, it's two proofs, and proof is probably the wrong word because I'm really doing more of like a proof outline because I'm not doing this fancy style. Let's just get right into it. So part one is going to say this statement right here, which says that the size of the natural numbers is the same as the size of the integers. Now, so I'm saying that this symbol right here is talking about the word size. You've probably heard this as about the word absolute value. The fancy name for the word size there, when you're in between two different things and you're talking about infinities, is going to be the cardinality. Cardinality. So the cardinality of a set is an infinite set, is how big it is. And furthermore, we're going to go ahead and put one more equal sign here. Anytime you're talking about cardinalities and sizes of infinity, there's a very special term that they use called aleph. Aleph naught. I've heard aleph as well, aleph naught. So you have a straight line, a squiggly n, and then a little zero. It's usually more squiggly than that. But this is going to be the size of what we're going to learn as is the smallest infinity. To start off the proof, I'm actually going to visually trick you. I'm going to say right here, here's my natural numbers. For those of you who do not know, the natural numbers are very, very simple. The natural numbers are going to be the numbers 0, 1, 2, 3, 4, 5, 6, so on and so forth, all the way forever and ever and ever. So that is going to be your size or your natural numbers. They go on forever and ever and ever. And we're trying to ask ourselves, how many is this? Well, clearly it is an infinite size. It keeps on getting bigger and bigger. No matter what number you give me, I can give you a bigger number. And because of that, we'd say that this is going to be infinity. Now, z, the integers, here's the part where I'm going to visually trick you. I'm going to go ahead and write that 0 in exactly the same spot, and then the 1 in the same spot, and the 2 in the same spot, and the 3 in the same spot, and the 4 and the 5 and the 6 and the dot, dot, dot all in the same spot. However, the integers also goes the other direction. It also goes into the -1 and the -2 and the -3 and the -4 and the -5 and the -6, and it goes on in both directions. So your intuition, your very first thought, and you're comparing these two sets, is it might be natural to think that the natural numbers is exactly half the size of the integers, maybe -1 because the zeros line up. So all of these numbers line up, and then all of these are extras, and because of that, you might say, hey, these two things are different sizes. However, it turns out there's a fancy little trick you can do. What you can do is you can say, you can create what is called a bijective function. What that means is there's one value here and one value here, such that no matter what, they line up with each other, and there's a one-to-one correspondence. When I say one-to-one correspondence, we're talking about how the 0 from the natural numbers, we're going to have the natural numbers on this side here, we're going to have the integers on this side, and I'm going to say the 0 goes to, because 0 is going to be an even number, all of our even numbers are going to have a very simple rule. You're simply going to divide them by 2. So 0 is going to go to 0. 1, however, is not an even number. For our non-even numbers, what we're going to be doing is, so just so you know the rule here, for even numbers, we are going to divide by 2. For odd numbers, we are going to add 1, divide by 2, and multiply by -1. So we're going to go ahead and add 1 to 1. That's going to be 2. Divide by 2, back to 1, multiply by -1. It goes to -1. Now 2 is an even number. The even number gets divided by 2. 3. The 3 is an odd number, so we're going to add 1 to it. 4, divide by 2, gives you 2, and it's going to go to -2. And then the pattern will continue on like this forever and ever and ever. So what's going to happen with 5 is going to go to -3. What's happened to 6 goes to +3. It's going to have to 7. It's going to go to -4. When you go to 8, it's going to go to +4, so on and so forth. You can't even see what I'm writing anymore. But the point is that I could also make this go the other direction. If I went the other direction, clearly I would simply divide by I can just simply, instead of dividing by 2, I multiply by 2, multiply by 2, multiply by 2, multiply by 2, multiply by 2. And likewise, instead of adding 1, dividing by 2, multiplying by -1, I can simply multiply by -1, multiply by 2, and subtract 1. So for instance, if I were to take this -3, for instance, multiplying it by -1 gives me +3. Multiply it by 2 gives me +6. Subtract 1 gives me 5. So on this side over here, it's going to be the odd numbers. So all the, oh no, positive numbers, sorry, positive numbers. Positive numbers, we are going to simply divide by 2. No, not divide by 2, multiply by 2. What am I saying? Get it together. And the negatives, we are going to instead, what did we just say we're going to do? We are going to multiply by -1. We're going to multiply by 2. We're going to subtract 1. And that's going to give us this 1-to-1 correspondence. Because we have this 1-to-1 correspondence, it must be that no matter which number you give me from the naturals, I can show you there's exactly one number that lines up with the integers, and vice versa. No matter what integer you give me, I can show you that there's exactly one number in the naturals. Therefore, our conclusion here, it must be true that the size of the natural numbers is in fact exactly equal to the size of the integers. Boom. That is part 1 of my favorite proof. Let me know if you really want to see that part 2 that shows you that there are different sizes of infinity. Thanks for watching.